do now is look at quality of service concepts. And the first thing I want to say about quality of service is if you have sufficient bandwidth, you don't need to worry about any of this. Sufficient bandwidth, we don't need to prioritize anything. Sufficient bandwidth, everything's fine. And I told you the story. I was doing it just cause, and it was before we actually were streaming anything. But the router said, "Hey, you can prioritize your video if you want to." So I did. And then I was doing web pages and downloading or doing something, and it just seemed a little slow. So I did a speed test, and the speed test came back as this is not right. And since I had done such a wonderful job of documenting what I'd changed, a few weeks later it said, "Oh yeah, you set the video." What it had done was reserved that amount of bandwidth for video. And reserved meant that nothing else could use it. It was in fact reserved. But quality of service concepts and the images here, two different things we can do is congestion management and congestion avoidance. Congestion management, we're going to prioritize the transmission of packets. Congestion management, what we do with carpool lanes, theoretically anyway. And the ones in the congestion management that get the higher priority in the carpool lane generally don't have the kind of congestion that us mere mortals do in the regular lanes where we're sitting in traffic. Congestion avoidance, and this just shows filling and then the maximum threshold and all that. We can conceive of this, I think, on the interstate traffic, again, because around here and in California is the first place I ever saw it, in the 70s actually. And probably in your area, where you get on the interstates, they now have traffic lights. So they regulate how much traffic can get into the stream of traffic, can get into the data stream, and that's what we're going to do with congestion avoidance. So instead of trying to regulate it after everybody's on the interstate or all the traffic is now trying to get into or is already on the data flow, the data path, will restrict what can get on. Turn the lights red, and then you stop, and then after a little while they'll turn green, and you kind of allow a little bit of it to get on at a time. A thing to consider about quality of service if you're using it, when you're using it, is you don't want to give some things so much priority that you lock out everything else. You want to be sure that your network continues to operate. Quality of service, kind of what it looks like, and the things that we would do here, we would consider. This says video streaming, general use, and in online gaming. One that would be in here if we're using voice over IP, voice would be at the top of the list here for traffic. It would be aligned or assigned in quality of service. But the one at the top where it shows the general internet jumping around all of these other things is we don't have any quality of service in this one. Everything is going to be a first in, first out, a FIFO sort of arrangement, so that we can, everything gets to contend for the bandwidth itself. Priorities, right? Yes, quality of service in VoIP, and all of them are going to deal with priorities. What kind of priority are we going to give things, or are we going to reserve, and what kind of priority system, what kind of quality of service systems are we going to use in these things? So in this one, the video streaming one down at the bottom, we're assigning the bandwidth with quality of service rules applied. Each of them gets a certain amount of the bandwidth, and video gets a pretty big chunk. Video needs some pretty substantial bandwidth in order to run, and it's going to be trying to always get more. It's kind of vociferous anyway. It is greedy, I guess is the word, bandwidth greedy that we do with these things. General internet use, if you're downloading or going to a web page, if you're delayed by a couple of microseconds or a couple of milliseconds, doesn't really matter. If you're streaming a movie or if you're having a phone call, those couple of milliseconds or 4 or 5 milliseconds could make a difference in the quality of the stream, the quality of the video, the quality of the audio. And in the online gaming, gamers are typically, they don't want to be interfered. They want to be able to have constant, reliable, steady configurations. And that's what we're really talking about here for the different types of service, for the quality, what kind of quality do we want to assign to each of these things. So again, what is it? Is the ability to provide different priority to different applications or data flows and to guarantee a certain level of performance to the data flow. And what this image is supposed to show and the output to me is it does a great job. We have the input, we have all sorts of different traffic coming in here. The red's going to be the high priority and the kind of orange is going to be the medium priority and the green is going to be the low priority. And then on the output, it appears that everything gets an equal kind of assignment, but the high priority comes out first, and the order that they would go in is what this shows. Typically what we're going to do is how many packets, how are we going to configure these things, how much data, how much gets to go here, how much gets to go there. The order, the one that's here, is typically going to be voice, video, and then the data that we use. Data, we need to have some bandwidth, but it's not going to really be time critical. Voice and video are going to be time critical when we do those things. Consistent and predictable performance is what we're looking for. You may be, what we're going through now, you may have been, or your family may have been streaming Netflix or Amazon or whatever else, and you really like for those things to be predictable. We don't, probably you don't at home, I don't at home, have an issue that we need quality of service because we generally have a whole heck of a lot more bandwidth than we actually need for these things. We can be at home here and I can be two different TVs. I can be streaming one thing in the basement, my wife's streaming another thing in the family room, and they don't interfere with each other when we go from one to the other. And each of them is going to have their own connection through the router. So sufficient bandwidth, again, back to emphasize, if we have sufficient bandwidth, we don't have to worry about any of this stuff. If we don't have sufficient bandwidth, then we have to do some prioritization. I'll go back to ECPI. When we first put in VoIP, we had a T1 line, 1.544 meg, which was red hot at the time. But when we got the voice, we reserved, I think, maybe 128K for voice. Voice is really important, but when you look at the voice packets, they're really, really small packets. We're talking, 20, 30K for each of the voice packets. A lot of them, but relatively small when we do those things. So what is it? Quality service, managed unfairness. Yes, we're going to be unfair because we're going to treat some things with a higher priority than other things. If we don't do anything, the default is going to be a first in, first out. Everything gets an equal shot at all of the bandwidth if we don't do anything. The things that we are managing or trying to manage with this, the services, bandwidth, latency, jitter, and packet loss. And what are each of these things? A set of parameters. Bandwidth, obviously we got the average number of bits from source to destination in 1 second. Latency is delay for these things. The time difference between the transmission and its receipt delay. And one of the things that I think that you can probably see delay is if you watch the local news and you've got the reporter in the field and they say, "Hey Jane, what's going on?" And that's the key for Jane to start the report, and Jane will be sitting there shaking her head, and then all of a sudden they'll start talking. But there is going to be a delay from one to the other. I told you we used to have satellite TV just to watch football originally until they changed all the rules. So we go to watch the football game. If it was a local game, you could have it on both the cable and the satellite. Satellite's 28,000, 30,000 miles in orbit. What you could do, and this is just to see, oh yeah, I can do that, is watch the kickoff on the cable and then switch to the satellite and watch it again. If you're doing streaming something, you may have different streams, may have different delays on those things. We've had basketball games that one stream was, it could be up to 3 or 4 minutes behind another stream to do those things. So latency is delay. Jitter, variability over time in latency. That's the numbers or the words to remember. It's an inconsistent delay, and that's the one where you get the choppy sort of audio or the choppy video that goes with these things, and then a packet loss, a loss or damage during transmission. Streaming is typically going to use UDP to go from one to the other. What we can do, and we can see these things, and you can see these things if you go to your video settings. Let me bring this over, and it's got me here, but if you go to the statistics and the settings, I can look at the audio here. I got the frequency. Latency is 193 milliseconds. So what I say is delayed by 163 milliseconds. Jitter is, and it just jumped from 5 to 7. The video here, 77 milliseconds. The video is better than the audio. The jitter, resolution, frames per second, and packet loss. Packet loss is good here, showing 0%. The screen sharing that you're seeing, 1280 by 1024, is what has been being sent at 11 frames per second, going up and down. Latency 287 milliseconds. So you gotta get the idea that when I change the screen and I talk about something that it's not there yet, is because the latency for the audio is different than the latency for the screen sharing. It just went to 101 milliseconds and the audio 151. So the screen would be ahead of the audio in each of these things. Jitter is an inconsistent. What it really is, jitter is an inconsistent delay, an inconsistent latency. The official term, variability over time in latency, which means that the delays are inconsistent. Another kind of bad drawing, if we send a packet, if we have a consistent delay, these things are going to be like this, if these are our data. If we have a jitter, we would send this one, and then we'd have a delay and send this one, and then maybe one right after it, and then we have a delay. These are the ones where you're going to get the kind of broken audio or broken video, is going to be if the jitter is not at an acceptable level. If that makes sense. Does that make sense, Michael? Yeah, I could talk for a couple of seconds, and that's why we get some of these other things to do these, to go from one to the other. And no, I don't remember max headroom. Okay, we get stuck, and it would get stuck for a couple of seconds. Yeah, and that's what jitter does for us. Because we have as long as the delay is consistent, latency is consistent, we don't notice anything. And even if you're watching a ball game and the delay is consistent, it's not a big deal because you don't know that. It appears to be live. If you're streaming a Netflix movie or an Amazon video, a TV show, or whatever you're watching, it doesn't matter. But when it gets stuck, the latency, the inconsistent delay, we start getting choppy video and choppy audio. That's when the latency starts becoming a factor for our videos and audios. And again, Back to the point that we've got sufficient bandwidth, doesn't matter because we shouldn't have any of these issues. The latency, the delay that you and I are getting probably from the ISPs and not from our local networks, because I'm on a gigabit, you're probably on a gigabit. Once I get to the router, I think that all of that happens from between the router and the website, or maybe some of it happens on the website that we're all connected to. Prioritizes traffic based on its importance using congestion avoidance method. That's what we're going to do with quality of service. We want to provide high bandwidth, less latency and jitter, minimal data loss, and then assurance that prioritizing one type of traffic does not affect the other types of traffic, that we don't knock one of them out. In other words, we give so much priority to audio and video, to phone and video, that we can't download, we can't see a website, we can't go to a web page, or we have to wait an eternity for that web page to open because we've assigned so much of our bandwidth to everything else that the browsing is going to be painful when we do those things. So the bandwidth and speed, here we have the amount of speed available for use, the bandwidth when we do these things. The speed of the connection, here we've got the gigabits per second over time, where we go from one to the other. Latency and jitter. Latency is delay over time. We'll go back to this one here. Bandwidth. As long as we are under the maximum, the speed of the connection, we're in great shape when we go from one to the other. And then we have the speed of the connection, and then latency versus jitter. Latency is the delay in milliseconds here over time. Jitter is the inconsistent delay, or the inconsistent latency from one to the other. The traffic types that we have, and this gets into the how much do we need to give everything. The TCP, the data, bursty and greedy. TCP will always try to take more of the bandwidth. It's always trying to make the window bigger, the data bigger, the more and the more and more. It's trying to take over the conversation. Takes as much bandwidth as it can. It's drop insensitive and delay insensitive, data is. Drop insensitive in TCP. If a packet gets dropped, we TCP simply asks that it be resent to us. Delay insensitive, yeah, you say, oh, this page is slow, but again, a couple of milliseconds, is it going to make a difference when you're downloading a page? 4 or 5 seconds, yeah, that's going to make a difference, but 10, 15, 20 milliseconds, which can make a difference in the voice and the audio and the video. TCP doesn't really care. So data is bursty, greedy, drop insensitive, delay insensitive. Voice uses UDP. It's not bursty. It's going to be delay and drop and delay sensitive, and one-way requirements for this. The latency under 150 milliseconds, and I think all of ours qualified under these things. Jitter less than 30 milliseconds. Packet loss less than 1%, and the bandwidth 30K to 128K. What I wanted to do, let me start Wireshark here, is I recorded a few seconds of a session some weeks ago, just so, okay, what are we actually doing? What's actually going on with these things? And I have a Zoom session in here somewhere. Zoom session. When I say these things are UDP, and that they're not very big here, we got data 7 bytes. 7 bytes here. TCP, and this one's TCP. This is an acknowledge. This is just, we may have a reinitialization of these things that's going on, but when we get into the data, 15 bytes, 7 bytes, 15 bytes. On and on and on, and then you can look and see what the data looks like in these things. And the data looks like in these things is something that doesn't make any sense to you and me, because I think that we're using encrypted transmissions to go across here. But generally speaking, as you go through here, the data pretty small. 142 bytes is the biggest one, but we don't have a whole lot of big data bytes. You can see the links over here in the LEN. Small, a whole lot of them, but they're small, and you can see the time over here. The time here, and how long it took to get these things. We're up to 66.71 seconds. So when I said a small amount of it, a little bit of what goes on here, the number of seconds. These are the frame numbers or the data numbers, the packet numbers, and then the amount of time that was spent doing that. But it is UDP voice, and this was video and voice combined together. The video, bursty and greedy. The video that we're talking about, I guess this was a meeting, probably the share would be the predominant thing in it. Bursty and greedy, drop and delay sensitive, one-way requirements, latency less than 150 milliseconds, jitter less than 30, packet loss 0.1% to 1%. Bandwidth is going to be a little bit more than the rest of them. The rest of them, the bandwidth for voice, 30K to 128K. Not a whole lot of bandwidth. And back to we reserved, and I remember, I think we reserved 128. It's either 64K or 128K for voice phone calls, because you always want your voice calls to be through, and it was reserved for that. Nothing else could use that bandwidth to do those things, except for the voice packets, to go from one to the other. So what are kind of some of the restrictions that go on for these things? The quality of service architecture, and down here, best effort is going to be the default. If we don't do anything else, it's going to be best effort. And the best effort services mean that I'm going to do my best effort to get it there to allow you to use things. And it's going to be a FIFO, a first in, first out for these things. 3 techniques for quality of service implementation. The first thing, and I'm going to do try to do a demo here in a few minutes when we go through some of the basics of this, is going to involve techniques to implement a quality of service identification and marking. What kind of traffic are we going to assign a higher priority, and what kind of markings are we going to put on it? We can do the other things down here. Best effort we can leave alone. Differentiated, we may assign a high priority, and then guaranteed a higher priority. In the voice, we'll assign the voice priority, and I think that it automatically, if it's a voice VLAN, will automatically give itself a priority of 5. But the management frames that we will use on that one are going to have a priority of 6 or 7, and that is 7's as high as we can go, because it's going to be on the switch when we do those things. Applying quality of service in a single node, the use of queuing, scheduling, traffic shaping tools to apply the QoS to a single node. So we're going to have different techniques, different methodologies, different ways to do this, and we're going to have different capabilities on switches than we have on routers when we look at them, and we'll look at what they're called and where they are in one of the later slides that we'll get to in just a couple of minutes, couple of slides down. Applying the policy and accounting functions in the network involves the techniques to control and manage the traffic. 3 levels of quality of service: best effort, differentiated services, and it differentiates traffics and applies quality of service on the traffic, and then guaranteed services. Guaranteed services, reliable transmission. Guaranteed services, we reserve a certain amount of bandwidth down there. Guaranteed, we reserve, nobody else can use it. Differentiated is we have different services with different priorities on the same bandwidth, same media, same interstate, I guess, that we would have for those differentiated. And the differentiated down here, best effort, IP, IPX, AppleTalk, the ones that we use. The differentiated services might be something like you're going on an airline, the differentiated first class, business class, coach class, different services, different levels of service, who can get on the airplane when would be available there. And then guaranteed bandwidth and delay. Guaranteed might be like a reserve seat versus when I used to fly, and I haven't flown in years, there were some flights that didn't reserve seats. Became a best effort. Everybody go find your own seat sort of arrangement. Who got on first, who was at the head of the line, obviously got the choicest seats. And if you were at the back of the line, you got the worst seats available for those things. Redundancy, guaranteed. Now, redundancy is if we have more than one thing available that we want to keep the connection. Redundancy would be like the first hop redundancy protocol. One goes down, we still use. Guaranteed is we have this thing, regardless if we have redundancy, one goes down, we still have the data flow. The data flow is the same, and the guaranteed would be we would reserve so much of the bandwidth coming out of whichever device was actually the active device at the time in order to do those things. Network classification, differentiating the different quality of services that we're going to use. And these can be on a per hop basis or on a network-wide basis. Per hop, the packet's identified at a router, but its class is not marked. The class information is not passed to other routers. It's going to have that kind of handling priority only on that router. On a network-wide basis, the priorities go from one to the other. In the IPP, DSCP, IPP, DSCP, the different things that are going to be the things that I can never remember. IPP, I've got it here somewhere, is the IP precedence. You think I could remember that one. The differentiated services control point, code point, I can remember. IPP, I can't remember. And then we have the layer, we can have these things, layer 2 or layer 3. Layer 2, class of service, and PCP, priority code point, are markings that go into each of them. And we're going to have a whole bunch of numbers later on that when we look at them, this is just the way that they get marked from one to the other. So it could be on a network-wide basis where the packet identified at the router and marked with the IPP or DSCP values for the network-wide are applied to the devices. And it just as an oh, by the way, in the Cisco environment, the devices don't trust each other. You have to configure them to do the trusting so that one device will take the markings of the other device from one to the other. Some of the common classifications, COS, class of service, IP precedence, the DSCP, the discretionary or differentiated, differentiated services code point. I could only remember for a little bit of time, or access control lists. And the demo that I'm going to be used to perform classification, we're going to match the access control list. Policy-based ratings, committed access rates, in-bar, all things that can be used for these things. The priority values to determine the quality of service to be applied to these things, to the traffic frames, and the priority used to classify the packets so that the packets of the same class can be forwarded with the same quality of service for these things. And the different ones that can be configured are down here. Layer 2, the class of service and the priority code point. And if you look at the table at the bottom, class of service ISL, the Inter-Switch Link Protocol, which we're not going to use anymore. We have to have the 802.1q or ISL if you have some really old devices in order to actually use the class of service, the quality of service classifications for these things. And then Layer 3, the IP value is the TOS type of service, and then the DSCP, the differentiated services code point. These are markings that are in the frames themselves when we go from one to the other. So what we do, the process, first thing we have to classification mark. First we're going to have to identify the traffic. Then we're going to classify it. We're going to mark it. And after we do that, we're going to create a policy. What are we going to do with the traffic once we've got it identified and marked? Maybe, identify, marked, get your first class ticket. What does that do for you? Now, what are going to be the policies? Well, you get to use the lounge or whatever, and you get to get on the airplane first, and you get to sit in these big seats instead of the smaller seats. For those types of things. And then what we have to do is apply the policy. So a multi-step, and I want to do a demo here in a couple minutes after we look at a few more slides on what we do with these things. So classification and marking determines what quality service treatment that the incoming traffic gets. The layer 2 class of service is a 3-bit binary field for these things, and then the best effort for these things, the manager here, the BE, the best effort, is going to be a 0 is the default. The classifications that we would get, and here it said voice V5, and the different, I guess, things that you might see and when we go through, and you don't have to know these, you just have to kind of know what this does when we go from one to the other. Classification marking, think of InfoSec on the documents, and clearance levels. We're kind of doing the same thing. The documents, the clearance levels would be what kind of service do you get? What can you see? And this is what kind of service can you see here. The PCP value, the primary code point, gives us the priority, and then the acronym for each of these things. The best effort, 0 is going to be the default for these things, the PCP. 0, 1, 2, 3, and then 0's after the 1 for these things. Background, BK on down the line. But if we go down here to 5 is voice. 4 is video, so voice gets a higher priority over video. 6 is going to be network control, and 7 is the highest, going to be the network control. So the management frames here, and this is the 7. This is going to be the class of service. This is going to be at the switch itself. The layer 3, the type of service, is an 8-bit field, and it's going to have higher priorities combined. Each of them gets a separate priority. Back to it, what are they combined? And you ever see one of these where the voice and the video aren't synced, like FaceTime, where the voice and the video aren't synced? I think probably FaceTime uses a different protocol. Well, each of them here, voice is going to get a priority of 5, and video is going to get a priority of 4. I think FaceTime probably combines the signals. I don't know exactly how that works when we do these things. What we're usually talking about here, and then we have streaming video and interactive video when we get to layer 3. Each of them is going to have a different priority that's assigned to it. And yeah, we get into they don't sync up, so maybe they're getting the different priorities. They're getting sent separately. Depends on how the application works, whether it's into consolidated signal or allows them to go separately. And I see the voice and the video getting unsynced frequently, and that has to do with the priorities that are assigned to each one of these things. So we have these things. The layer 3 and then layer 2 is going to have a different priorities than layer 3. Assigns a precedence to each packet, the IPP, the internet, the IP precedence, the most significant 3 bits, and then maps the packet to a particular forwarding behavior. The differentiated services code point is the most significant 6 bits. When we look at the type of service, you're going to say, okay, this is crazy when we get to a couple of charts here. The DSCP is concerned with the flow of traffic, the source IP, destination source, destination port. The classification procedures, the packets are classified according to the DSCP, separated into queues, marking or closer examinations, and then we can do shaping or dropping. We'll have one of those. Shaping is when we buffer information. Shaping can result in delay and jitter. So we don't want that for our voice packets, for instance. Data, we don't really care. Shaping is when we exceed the limits that have been specified, the data limits that have been specified. We buffer it until we have enough bandwidth to send the information. Shaping is when we get above the limit, we drop it. TCP will ask for a resend. The precedence values are going to determine the class of these things: routine, priority, immediate, flash override. Some things that all of you Army and Air Force guys, and none of you are Navy, have seen before: the routine traffic, priority traffic, immediate traffic, flash override. Whoever did a lot of this stuff probably had a military background. And remember that the DARPA net, the Defense Advanced Research, did most of all, or did all of the development for the internet. So a lot of that would have come from people with those kinds of backgrounds. This is the one that says going to drive you crazy. Do you have to memorize this? Absolutely not. It's just that, yep, there's a lot goes on in this classification. On a per hop, behavior, drop forward, or reclassify. So we can configure the policy to forward it based on whatever the circumstance is, to drop it, TCP will ask for a resend, or to reclassify it. Say, oh, we'll just put you in a different queue. We'll make you a lower priority. You had, or maybe a higher priority. Kind of issues with your ticket. Maybe you come in and say, or if you're flying in uniform, maybe, and I don't think they do it anymore, but occasionally they used to. We have an extra first class seat. Would you like to have it? So you can get reclassified at some point along the system when we do those things. DSCP consists of a behavior and a drop probability: medium drop, low drop, medium drop, high drop, and we have a marking that goes into the layer 3 packet that is drop eligible, where we can mark these things. So different priorities, what are the drop probabilities for each of these things? Different priorities, different systems are enabled on these things. And this one goes through a whole lot. Assured forwarding, what is the coding going to look like? AF32 is its DSCP. If you look in Wireshark, it'll show you, you have the DSCP. If you have any markings in there, all of mine are just the default. They don't have any on there because I've tried to set up GNS3 to do some marking, but I can't get something on the other end that has a browser that would send the traffic that I would need in order to do that. So I don't have any that have markings. IPP011 is going to be a class 3 for these things. A DSCP01100, and you can see all these things over here. The behavior is 3, and the drop probability is 5. So all of that is going to be part of the binary configuration of these devices, and when we put it together we have the whole thing. Table here, interesting table, something that just gives you an idea of what can go on with these things, to the markings that can happen with them. Again, not anything that we should have to know for the CCNA. And you can look at the and here we have the critical, routine, priority, immediate, and flash override, the different priorities that would be in each of those major classifications. The device trust, the Cisco interface for these things, the configured trust, the DSCP and IP packets, when the trust is enabled, the device is said to be in the trusted interface, and I think that, let me draw see something in here, and let's see if we can see what's going on. And that's not what I wanted to do. If I can remember the commands, and as you know, sometimes I don't. So let's do show MLS QoS. And then we have to do an interface fastly at 0, 1. And what it says, and this is just the command that you have to use. It doesn't make any sense to me. MLS multi-layer switch. QoS I get, quality of service. Interface I get. QoS is disabled. When it's enabled, the following steps will be applied. The trust state is what I wanted to see here, not trusted. Trust mode, not trusted. I can enable it, I think, MLS, QoS, and then carriage return on this thing, and let's do show MLS, QoS, fast Ethernet 0/1. I don't think it's going to do what I want. Let's go back where we can use the question mark. Show MLS, QoS, and interface fastly at 0, 1. And I think I have to enable that. Still not trusted. FAT MLS QoS, and then it just gave me QoS, and then just the keyword here. So anyway, you can enable it. Let's go to the interface fastly at 0, 1, and do MLS QoS, and then here's where we turn on the trust, and then trust. You do it, and I should have remembered that. Do it one interface at a time. And then if I do the show MLS QoS fast Ethernet 0, 1, and show MLS QoS interface fast Ethernet 0, 1, then I have trust DSCP, which is going to be different. Now I'm going to jump over to another one. There is a mapping, and it's going to be in the. I got something. I got to draw. I got more than I couldn't grab it. When we go here and here, we'll just do. Oh no, that's the wrong one. Let me get. I'm grabbing too many things at the same time. Down here, I have R1. This is what I was looking for, the DSCP to COS map. There is a map that goes in both directions. It'll map the layer 2 priorities to layer 3 priorities, and layer 3 priorities to layer 2 priorities. Not that you need to know that, not memorize that, but yeah, there's a map. If we go from a switch to a router, there are different markings, different locations. How does that work? Well, there is a map that if we establish the trust, that's going to map the one to the other when we do those things. All Cisco devices are in an untrusted state by default. Different math to classify the incoming packet. Trusts are configure the interface to trust the DSCP values, to trust the COS to DSCP map, the one that we just saw, and then apply a standard or extended access control list to classify the packet. The steps that are involved in this, and this is where I want to try to do my demo, is ID the traffic, classify class map. Class map is when we define the classes of traffic. What traffic do we care about? And we're going to use the access control list in order to do that. Then a policy map. What are we going to do with the traffic? And then after, what are we going to do with the traffic? We need to apply the policy. We're going to apply the policy at interfaces. So let me drag this back over here, and yeah, I'm going to have, because I have to keep the different things sorted out with a lot of different steps in this thing. It's a kind of a logical process, but a lot of different steps. And I didn't invent this when I got it off the internet, but the issue here is my boss man on his computer said that if I ever can't get onto the internet, you might as well update your resume because you're not going to be here very long. So what we want to do is to configure our devices so that the boss is always going to be able to get onto the internet. And we've got two routers here, and we're going to have one, we'll do an input policy, and another one we'll do an output policy. So the first thing we need to do is identify the traffic, and we're going to do that with an access list. And I guess if I was in config mode, it would help. So we're going to access list, and we'll just use one here. And yes, we haven't done those. Security tomorrow, late today and tomorrow, we will do those. And we're going to permit host. We're going to permit his IP address, which is 10.10.12.2. So we have now configured that. The next thing that we need to do in this scheme of things is to do what's called a classification map. What traffic do we care about? So we're going to classify his traffic here. So what we'll do is in config mode, we'll do a class map, a classification map, and then the question mark here can do a word or a match all or a match any. And we're going to call his class map, we'll call it boss. And then what we can do after that is we got description, exit, or match, or a no. We can match, and what we can match here is an access group, an any, a classification map that we have, another classification map, a class of service, destination address on down the line. What we're going to do is we're going to match an access group, and access groups are going to call the access control list. When I say match access group, it's going to use that access control list. So it's going to match everything. His IP address is really what we're talking about here. So after we do that, what we need to do is a policy map. What are we going to do with this traffic? So let's go back to this guy, and what are we going to do with this traffic? We'll do a and config POL policy map, and then a word, we have to give it a name, and we'll call the policy map boss precedence. We'll call him boss precedence. And then what class, the criteria, what classification map are we going to use? And the classification map we're going to use is boss, the class map boss. And we have the class policy. We can look at class, the question mark here to see what is there, the word, or we can use the default. And the word that we use, that we did for our classification map to determine which traffic we use, was boss. Now after we get to that, what are we going to do with this? We can do bandwidth, exit, no. What we're going to do is set a precedence level. And the precedence, we have all the ones that we had, the 0 through 7. We're going to set a precedence of 5. So what we have done is identify the traffic in this thing, and then said what we're going to do with the traffic. What we haven't done yet is to apply that policy. And we're going to apply this policy as it comes into the router here, and I think gig 00 for it. So we can do exit here, get out of this, and let's get back to the config mode. Exit took me up one level at a time. So now I'm going to go to interface gig 0/0, and I will do a service policy, and service policy input or output as it comes into here. And then what do we want to do? And the word here, the policy map, was boss precedence when we do those things. By the way, if you try to use one of these and you haven't configured, it'll say it's not there. So what we've done in here as it comes in, we have marked it with a precedence level of 5. Now what we need to do is something with it so that we can put it out here on the internet when we go from one to the other. It's still going to have, we may not trust that precedence, but we are still going to have those markings as they come in to this thing. So on the second router here, config T, we're going to do a class map. What map are we going to do? Class map. And the class map we're going to call here is boss precedence 5. And what we're going to do with it, we can do the match again, but instead of match the access group, we're going to match the precedence, because we know that the boss's traffic is going to be matched with a precedence of 5. So PRE, precedence 5. So all the precedence 5 traffic is what we're going to get here. So now we have determined the traffic again on the second router. So we need to do a policy map again, and we're going to name the policy map, and we'll call it boss bandwidth to get there. So the class map that we will use was what? Boss precedence 5. You see why I have these things written down over here? A lot of different steps. Just to show you if I did something wrong, it says, it's not configured. I can't use that one. So boss precedence 5 I can use, and now what I can do in here are a number of things: bandwidth, exit, priority, random detect, set, on down the line. I'm going to assign a bandwidth. I can do a percentage or the remainder or a specific level in kilobits, and the kilo here is significant when you write it in kilobits. So but we're going to do him bandwidth, and we'll do percent. We'll assign him 20% of the bandwidth. So he now has 20% of the bandwidth reserved as soon as we apply this thing. And this one, interestingly enough, we're going out is gig 00. So just so that you're not doing it on the wrong interface here, we're going to go into the config T and do interface gig 00. So as it goes out of this interface, the service policy is going to be an output boss bandwidth, so that now the boss will get 20% of the bandwidth as he goes on to the internet, and we're not going to have to update our resume to go from one to the other. Again, a lot of steps, but it's kind of a straightforward process if you do it a few times. And yeah, right now it's like probably your head swimming a little bit with all of this different things, but the whole thing in a different terminology that we use for these things. So the terminology, we classify the traffic, we configure a policy, what are we going to do with the traffic, and then we apply the policy so that the policy becomes effective for these things. So this is just a listing here. Defining the class map actually ought to be up here at the top when we do this thing. We're going to the policy map associates a traffic class with one or more policies, and then we can have a maximum of 256 classification statements, and then the class map down here classifies the traffic. Well, first we're going to classify the traffic, and then we're going to assign a policy to it. Input policy maps mark the traffic that are received at the interface, can drop drop packets that do not conform with the permitted rates that go on with this thing. So we're going to drop the packets if we want to. When a packet exceeds the limits, priority level can be reduced. It can be marked down. We can have up to 32 classes, and then a default class is defined as a class default. And the defaults for all of these things are applied or used, and the default is used when nothing else is available. Default route, nothing else is available, we'll use the default route to go from location to location. Output, scheduling and queuing mechanism on packets at an outgoing interface. Access groups are not supported in the output policy maps, quality of service actions in the output policy map, the queuing, the waiting, the bandwidth limiters, shaping limiters, and we can have a default map here also. And again, default if nothing else applies. Only those packets that are already matched by an input policy map are matched to an output policy map. We could do both the input and the output on the same device. And this particular one, we happen to do it on different devices so that everything came in with a 5 that going out got assigned, got put into the 20% bandwidth available. Same image that we had a little bit earlier. We're going to talk a little bit now about congestion management, congestion avoidance, what we do with each of these things. And congestion here, inevitably congestion occurs. I don't think that it really is inevitable, but if it does, we need to sort out the traffic and the different queues. And let me go ahead and put all of these up here. The queues are the different lines, the different streams that the different data types use. And this LLQ is low latency queuing, and this is going to have a scheduler that works internally in the device. All of the voice and the video and the data are going to come into the router here at the same time. Once we've enabled, configured quality of service, it's going to have a scheduler, and the scheduler is going to then use one of the different types of queuing mechanisms that are available. Round robin just goes, one voice, one video, one data. Weighted round robin may go one voice, one video, one voice, one data, one voice, one video. So that in this case, hopefully you see that I said that right, that voice will get twice as much as everything else. Or we may have a voice, video, voice, video, data. However, weighted round robin is we can assign more bandwidth to one and to the other. Low latency queuing means that latency, we want to minimize the delay that happens with these things. So we're going to have queues, we're going to have a scheduler that will schedule or assign time slots, and we are talking about the time slots, time multiplexing in order to send these things out over the same piece of media. The considerations data classified based on the importance to ensure that business critical applications don't suffer data loss. And one of the things that we do have to be sure of is that we don't wipe out certain classes of traffic, so that we're so intent on being sure that the phone calls are good and that the video streaming is good that now we can't update the database, or we can't let we don't allow our salesmen log in from remotely using the VPN to update the databases. You have to take all of that into consideration. Some different things, DSCP, the application, the network control traffic, and these are some of the classifications that might be put into the DSCP, things that you will see. VoIP, EF, and the EF traffic up here, we're assigning it 30% of the traffic. All the other traffic down here is going to contend for the remaining 70% of the traffic. Different things that can be available here. Class-based weighted fair queuing is used as a scheduling tool for prioritizing data applications. Video, high bandwidth. Priority queuing with LLQ, low latency queuing, is the preferred prioritization for interactive video conferencing, Zoom. Voice, priority queuing with low latency queuing, preferred with interactive voice transmissions, and class-based weighted fair queuing for non-interactive voice transmissions. Kind of, I guess ours is a non-interactive voice transmission, and you don't have to really worry about the the voice and the video, and I don't know if they are or not. And if you turn on the video, I've got the camera on. Are they synchronized? I don't have any idea. I was watching a meeting the other day, and it worked really good for a while, and then the longer it got into it, and this was being streamed over Facebook, and the voice and the video and the audio got out of sequence, and those become pretty obvious to you. And when we look at those things, back to the differences, they're going to have different priorities for those things. The queuing mechanisms, the FIFO, first in, first out, not good for voice or video. The voice packets can be delayed by the large packets, and we can see these things that even with the priorities, that some of them may be delayed more than the others. Priority queuing, in this one, the lower priority queues are served after the higher priority queues are empty, and this is one where we may have low priority starvation. We may have data starvation in order to do that. In other words, we have so much high priority traffic that we never get to the low priority traffic. Custom queuing, 16 queues in a weighted round robin fashion. It can introduce delay and jitter, and as you can see, each of these got an upside and a downside. Everything in networking, I think, has got an upside and a downside. Weighted fair queuing divides the bandwidth by the number of flows. No bandwidth guarantees in this one, but the latency can occur with the high priority traffic. And then the class-based weighted fair queuing guarantees bandwidth to certain classes. The high priority traffic is not going to have latency in there. This is just the different mechanisms that can be used for these things. This is a priority packet. When we go in here, we got a priority of 5. And here 802.1 queue, and again, we've got to have 802.1 queue in order to do that. And down here in the IPv4 header in the differentiated services, code point field, we have expedited forwarding marked in it, and you can see the binary. And this is just so that you can if you look at these things, you can see these things, can see the priorities. Reduce the congestion at queues by using the TCP windowing techniques, and we talked about those. When the queues are full at the outgoing interface, packets at the end are going to be dropped, and this is going to be called tail drop when we do those. We're going to set thresholds for these things. We have the queue depth, that if we're okay, 0 to 300 packets, we're within the allowed, the number of packets is less than the minimum threshold, then everything goes. If the number of packets go between the minimum and the maximum threshold, we're going to drop a percentage of the packets in the tail drop. Once we get above the maximum threshold, then we're going to drop all the full queue. We're going to drop all the packets until we can get back down into a no action or drop a percentage of the packets that go from one to the other. Weighted random early detection on these things. We have a flow one, we have tail drop on these things, and then if we increase the window size increase. Over here the window size is increased, and here maybe the window size is decreased to do these things. How much traffic is going to go from one to the other. And in this one we've got the two flows. What happens to the traffic? The tail drop on these things, the tail drop, everything that gets above the tail drop is defined here. Everything that gets above the maximum is going to be dropped with these things. And there's a lot of explaining for things that you just need to know conceptually for what goes on. Policing controls the burst E traffic. Makes sure the designated flows get the correct bandwidth for these things, can change the precedence of the packets, and chop off the excessive flows. Policing, just when we get above a certain limit, it's going to drop it. Shaping is going to buffer it and send it later. Uses ingress tools. We can have two types of policers. We can have individual, aggregate, actually three, and then unconditional priority policing can be enabled on these things. The types of policers for the categories. The traffic shapers are at the outgoing interface, and the traffic shapers can be used to buffer excess traffic so that and bandwidth, the available bandwidth goes up and down, varies from one to the other. The shaper is going to buffer it, and then when we get sufficient bandwidth available, it will send the traffic that we have. Shaping rates and schedule the transmissions for these things ensures that the transmission rates do not exceed the specified shaping rate. And class-based weighted fair queuing or low latency scheduling is used to manage the queues for these things. Kind of an image for what these things might look like. Policing here, when we go above the target, it just simply chops it off, drops it. TCP will ask for a resend. Over here in shaping, the rate limit, when it gets above, it buffers it, and then when we go below the maximum bandwidth, it's going to send that data. It's okay for data, not real good for voice and video because it can introduce delay and jitter for these things. So kind of a summary here. Policing, drop or remarks the traffic. There is no buffering. We have TCP retransmissions. We don't have a jitter and delay. We may have something missing, but we don't have jitter and delay. It is a harsh sort of way to handle the traffic and uses retransmissions. The shapers drop or delay traffic, and we're going to have jitter and delay in those things. But it is considered the gentler way to approach these things. There are now number of labs here, but what I want to do, and I've got them consolidated at the end, and this is where a lot of the slides come in for these things. I've got these at the end. What I'd like to do is go ahead and finish the slides up, since there really aren't that many left, and then we'll get into the lab. Troubleshooting networking issues, and we talked about some of these things before. The issues that we can have with these things, client configuration or connectivity, name resolution, DNS issues. Can we get to the DNS server? Is it working? Can the DNS server get out of the network in order to do our iterative lookups if we need an iterative lookup? But client configuration can be one of those things. Do we have the correct IP address for the DNS server? Can we get to it? Can we ping that server? DHCP configurations, DHCP functionality can be issues. Another slide here that kind of goes into these things. And the source NAT and end user NAT, NTP issues, all things that can happen here. And then the DNS server settings, the host to server connectivity. Do we have the right IP address? Can we get to it? Can we ping that IP address to get from one to the other? DHCP, if we are on the other side of a router, DHCP relay agent, do we have the IP helper address configured correctly? Do we have network addresses for each of the scopes for each of the networks that we're using the relay agents to? Is the address pool depleted? Do we have a sufficient number of addresses available in it? We don't have a conflict between dynamic and static address assignments. We've configured the DHCP server to check to see if that address is already in use before we assign the address, so we don't get into a duplicate IP address configuration issue. Server-to-server communication. This is if we have multiple DHCP servers on the same network so that they can communicate with each other and they know which ones gave out which addresses, so that, again, we don't get into a duplicate issuance issue for these things. NAT issues, correct configuration. Are the access control lists configured correctly? Because That's another protocol that we use to access control lists in order to define who could get a NATed address, who could get a public address. The correct routes are identified, and one of these, can we get back to our public addresses? Is there a route back to the public addresses? And this is one of those, you may be able to get there, but can you get back? You always have to be sure that routing works in both directions. What networks are permitted by the access control list? The NAT address pool is not depleted, and if there is any possibility of that, we have the overload statement. And I think that you should always use the overload, because you never know when you're going to get a high demand for addresses to do these things. The router interface definitions are set correctly. The IP NAT inside and the IP NAT outside, so that when we NAT inside, we're actually NATing the inside interface to the outside interface from one to the other. So all of those definitions are going to be correct. NTP, the appropriate commands, the server, we have the correct server configured to take our time from. Can we get to the correct server? Does the server have the correct time? Is it getting it, when it's NTP server providing us, is it getting accurate time from one of the other resources or from another resource that gets directly back to a Stratum 1, Stratum 0 device, so that we can have the most accurate time that's available to us. And again, a bunch of different lab sort of configurations and the troubleshootings that go on with this. And the last set here, the troubleshoot the management issues, SNMP, Telnet, and SSH. For those, verify that the agent services are running on each agent device, that we have SNMP enabled on the device. And we looked at a router, and we could set the SNMP server, and when we do those configurations, that activates the agent on the device. That the community strings match, that we are using the same community string for all the devices that we want to do, and this is obviously for version 1 and version 2. Ports 161 and 162 aren't blocked by an access control list, that the information can get to us. When I did, and I told you, I configured SNMP on my workstation here so that I could get that information over there. I had to configure the community string, and it kind of is a pain to put it on Windows. Windows really wants you to use the Windows management protocol to look at all of those things. But the different things that happen at SNMP, community string being the big thing, our bosses locked us out by putting a different community string in the SNMP server of the devices that we were looking at. So we had to find that community string. Once we found it, we were in business. They could have made it a little more complex, I guess, or difficult by configuring access control lists and maybe specifying the address of the network management server so that it would only send it to those particular ones. Telnet, we've talked about it, protocol that we really don't want to use unless we absolutely have to, but if we use it and we have issues with it, can we get to the address? And it's always, can we get to the address? And this is where ping comes in. Or traceroute. Traceroute, again, if you use it where it fails, start looking there on that particular device. Verify the transport protocols, and the Telnet is the default transport protocol. Credential information. The default configuration on the routers and the switches have a login command. And if you try to log in with just a login command, it'll tell you that login is set but no password is configured, and you can't log in until you set a password with that login. If you want everybody to be able to get there without actually logging in, use the no login command. And then all you have to do is telnet to it, and you're automatically on it. And oh, by the way, you can't get into privileged exec mode on a telnet session until you have configured an enable secret password. The secret password has to be configured, or a password has to be configured on the privilege exec mode, and you can't do that from a remote session. So you have to, if you're actually going to do configuration, you have to set the password before you get there. Verify that access control lists permit the traffic and that the VTY lines are available. Port 23 is open on the system. SSH, the clients of the devices, the login command, the key size. The older versions of SSH don't have a long enough key for the newer version. So if you configured SSH version 1 and used a short key length, SSH version 2 might not work because the key length is not long enough. And then in the verify the access control lists will permit the traffic to go from one to the other.